Hello, everyone. I'm Rui Liu, an undergraduate from University of Electronic Science and Technology of China. I'm very honored to be here to present our work. This work was done with my advisor De Fulian, also from UESTC, and other collaborators. Thanks again, and now let's start. Recommender system is an effective means to help people filter unimportant information in the era of information overloading. For example, Google News recommender system must serve for millions of users by choosing personalized articles from millions of articles based on their click and search history. Another example, Amazon needs to recommend products tailored for users' taste from more than 480 million products. It's commonly said that real-time recommendation is the key to the success of online business. But why? The reasons are simple. Users' interests are always evolving and new items are always emerging. However, given the large number of users and items, it is challenging to generate real-time recommendation. So how can we get our real-time recommendation results? Is it possible to pre-compute top K preferred items for users? We assume there are M users and N items, and we recommend top K preferred items for each user. The time complexity will be Mn log K, which is quite a great challenge. Of course, we can resort to distributed or parallel computing techniques, but we need a lot of machines for computation, making this solution expensive. To this end, we study an economic and effective way for generating real-time recommendation. It is well known that matrix factorization often generates the best sum model performance, so we take it for this study. Based on the learned latent vectors of both users and items, we apply the sign function to map them into 1 or -1. When using binary codes representing users and items, we can save memory consumption significantly. For example, 10 million products would occupy around 20 GB space when using continuous latent vectors, while representing them in binary codes, only 640 mega space is needed. In addition, we can fast compute users' preference for items based on Hamming distance, because it can be computed efficiently by XOR, the operation on the instruction level. Based on their comparison, we can see that hashing methods can achieve up to from tens to hundreds of speed up. Now, let's go through some related work about hashing methods. Hashing methods for recommendation system is to encode real-valued latent vectors with compact binary codes. Previous literature can be classified into two groups. The first one is two-stage solutions, such as binary code learning method for collaborative filtering and preference-preserving hashing. Learning binary codes is generally NP hard due to its discrete constraints. So these two-stage solutions often first solve a relaxed optimization problem by discarding these discrete constraints and then perform a direct binary quantization on it. But it will result in large quantization loss due to its oversimplification. So the other method, mixed integer optimization, represented by discrete collaborative filtering, can solve this problem well. It can be used to direct discrete optimization problem. Although a lot of work has been done, there are still three challenges existed: cold start problem, implicit feedback, and classification. In our work, we propose a new framework called Discrete Content-Aware Matrix Factorization, short for DCMF, which can be used to solve cold start problem by incorporating user and item content information into our total framework. And we also aid an interaction regularization. I think this. We also aid an interaction regularization term to make our model suitable for implicit feedback. I'm sorry. We add an interaction regularization term to make our model suitable for implicit feedback datasets. And our model also support for classification tasks by finding a variational upper bound for logic loss. First I want to introduce how to take content information into account. From business website, we can see that each movie has been labeled with some genres like comedy, action, etc. And in Amazon website, we can see that there are many reviews for each product. So for movie, we apply 0-1 coding, and for products on Amazon, we collect their reviews and apply text processing, TF-IDF, in order to get item feature. In order to solve for our objective with item feature, we add two terms to the loss function, and same for the users. Second, I will introduce how to obtain our interaction regularization term. In weighted regularized matrix factorization, the loss function is like this, where W subscript ij equals alpha plus 1 if user I has rated item j and equals to 1 otherwise. The loss function can be written at this form under our condition. By a simple derivation, it turns out to be this. We know that here alpha is usually far greater than 1. So the loss function approximately turns out to equals to this. And the second term is just the interaction regularization term. Third, I will introduce how to solve for classification. We first apply logic loss for classification like this. After simple derivation, we find variational upper bound for logic loss. Lambda x is like this. And here, this figure shows the curve of the function log 1 plus ex, and its upper bound at x equals to 4. As we can see, this upper bound is tight and quadratic. So here is our total framework. It consists of many terms, and each term has its own function. First, these two terms can help solve code star problem by learning user and item binary codes from features. And as mentioned before, the last term is the interaction regularization term, which can make good use of implicit feedback. And our loss function can be different forms under different tasks. Finally, we have balance and decorrelation constraints to help the learned binary codes distribute well. After obtaining the objective function, we apply alternate optimization to update phi, psi, p, q, u, and v effectively. We focus on updating for each user I in parallel, so we ignore terms irrelevant to phi plus subscript I. Then the objective turns out to be like this. Then we develop a coordinate descent algorithm to take turns to update each bit of hashing codes, phi subscript ID. And the new value of phi subscript ID equals to 1 if phi subscript ID hat is a positive number, and equals to -1 if alpha subscript ID hat is a negative number. This is the update rule for regression tasks, and for classification task, since we have found quadratic, it's a variational upper bound for logic loss. So there, the update rule for phi is very similar, and it's totally similar for updating per psi. When fixing phi, other parameters, learning P can be solved via optimizing this objective function. With the help of a centering matrix J subscript n, we apply SVD to this, and we got S subscript P and T subscript T, which contains the left and the right singular vectors respectively. For D2 dimension, phi is not full column rank. So we construct S subscript P hat and T subscript T hat by Grimes-Schmidt orthogonalization. Finally, we have the update rule for P. And the objective and update rule for Q is similar to P. Again, we're ignoring other parameters and terms irrelevant to U and V. The objective for U, V is like this, and then this is the final update rule for U and V, respectively. Now, let's discuss our experiments. We evaluate our proposed model on 3 public datasets, MovieLens, EAP, and Amazon. The basic statistics of these datasets is shown on the table. And the recommendation performance is assessed by widely used metric. We use NDCG for regression task and mean percentile rank for classification task. The formula of percentile rank is shown on the right. And here, intuitively, PR subscript MN equals to 0 means item N ranks number 1 in the preferred list of user M, and it equals 100% when item N is the last preferred item of user M. To evaluate our model better, we choose 2 baselines for comparison. One is the state-of-the-art method DCF, which is used to compare for caching-based collaborative filtering. The other is libfm, which is the best SOM model for feature-based recommendation system. In our experiments, the results of in-matrix regression are shown on the screen. From these 3 figures, we can see that the red line indicates the performance of DCMF, and the blue line indicates DCF. By comparing red line with blue line, we can see DCMF outperforms DCF in all 3 public datasets. Also, this black line indicates DCMFI, which is the initialization results of DCMF. So by comparing with red line with black line, we can see it demonstrates the effectiveness of mixed integer optimization algorithm. These are our out-matrix regression results, which is used to simulate the code star problem. Under such a condition, the DCF doesn't work. And as we can see, with the increase of the length of hashing codes, the performance of DCMF could approach and even surpass that of libfm. So we can see it can help address cold start problem well. Also, again, comparing with red line with black line, we can see the effectiveness of mixed integer optimization algorithm. Finally, let's see our classification results. These are our total results, and I will interpret it more clear. First, these three bars means from left. The first bar means the initialization of DCMF with continuous latent factors, and which removes both content information and interaction regularization. And the second bar removes just content information, and the third bar removes nothing. So based on the comparison among them, we can show the effectiveness of both content information and interaction regularization. Second, by comparing DCF with DCMF, we show the superiority of DCM to DCFM. And third, again, by comparing with the initialization of DCMF with binary codes, with DCMF, we show the effectiveness of mixed integer optimization algorithm. At last, by comparing DCF with libfm, we show on the first two sparse datasets, Amazon and Yelp, we show the superiority of DCMF to libfm. To sum up, in this work, we propose a new framework called DCMF to hash users and items, and incorporated content information and implicit feedback into a single framework, support for both regression and classification tasks. We also develop an efficient mixed integer optimization algorithm and show superiority of recommendation performance in 3 public datasets. That's all. Thanks for your attention.